Did somebody tell you about the performance parameter of the heat pipe so far? How do you compare between heat pipes? We are coming to the end of this workshop. How do you, so there will be some use of me talking to you if somebody has not told about it. How do you compare the performance of heat pipes between? Is there anything like an efficiency or effectiveness of the heat pipe? Somebody has told already in this, from today, this morning onwards?
No.
You might be knowing it elsewhere because sometimes before you may have thought about it. So it's so simple. I have a heat pipe. It's functioning as a heat pipe. What is the measurable quantity that I have? What is the temperature along the heat? Another one is the amount of heat that is transferred at steady state or transient state. What? If I simply take the ratio of the heat throughput divided by delta T, temperature difference across, this is called a conductance. Okay, and the heat pipe has got a characteristic. Say whatever other conductor, simple conductor you take, you increase the heat throughput, the temperature drop also will increase. Whereas in a heat pipe, what happens is that as there is circulation, by now you know, inside you have the circulation, the fluid, the velocity is developed, and then the heat pipe effect. The more and more input you give, it becomes a better circulating device, and the temperature becomes flatter and flatter. This means if I calculate an effective conductance, this effective conductance increases with the increase in input until you reach the operating limits. You already know about operating limits, is it not? So you reach the operating limit means it no more functions. So it's always better to operate the heat pipe as close to operating limit as possible because that is the situation which gives the best effective conductance. Now hope you understood also what is effective conductance. That is one method. Another one is an effective conductivity. It's so simple. You just consider the heat pipe to be a conducting rod and compare what is happening in the heat pipe to Fourier law. Fourier law is more or less like this, the Ohm's law, basically for heat transfer, is it not? So you simply you compare with the Fourier law, minus k dt by dx is equal to q, you will get a k. That is an effective k. The heat pipe is not a conductor, is it not? So this k effective, which can be brought out by an analogy of what is happening in the heat pipe to the Fourier law, can be used as a good parameter in order to compare between heat pipes. You sometimes compare it with the material of the heat pipe. The material of the heat pipe is copper, I say K effective ratio. K effective divided by K of copper. I say 5. Means the heat pipe is operational 5 times better than that if you had used copper, a simple conductor. And it's not 5 and all, sometimes you go to thousands. Because the thickness of the heat pipe is so small, you got what do you mean by telling that? The thickness of heat pipe is very small, means that it's through a very, very thin conductor that is, this heat is getting conducted otherwise. It is not going to happen without a large temperature drop. Whereas here, it is not a thickness which comes in. It's not an axial conduction through the material, but it is a conduction because of a total effect of this circulation inside. So what is not there in a heat pipe? You have everything in a heat. You have the convective dissipation, you have the phase change, you have the conduction, you have radiation if you have. So all this totality effect is what is coming out finally as an effective conductivity of the heat. So this effective conductivity is the most important performance parameter. So some of this, so in order to calculate that what is required, I require the heat throughput measured. I should also have the temperature drop. This is not. That is why I use my temperature drop in my calculation. If I assume that the heat pipe is isothermal, if I assume that in my calculation that the heat pipe is isothermal, I am never going to get this performance parameter. So I have to find out what is the temperature drop along the heat pipe. That is how small it is. You have a big question, then keep it for it.
Simple question.
Yeah.
Denominator, the temperature difference, the denominator for the effective conductivity.
End point temperature difference between the ends. Please keep your questions today, and because others might not be interested. Also, we have only a very short amount of time. I am given an ultimatum to finish my lecture by 5:15. So let me finish that first. I'm sorry about that. I would have liked to discuss. So these effective conductivity and its parametric variation. What happens when